Hello everyone, welcome to the Real Programmers. Today we will talk about the solid principles. If you are already familiar with solid principles, this video will deepen your understanding about these principles. Let's get started. In this video, we will first talk about the definition of solid principles and also why you should learn and follow these principles. It is best to understand these principles with some context. Keeping that in mind, for each principle, we will cover its definition, then Java code examples showing the violation and resolution, and then the significance of applying these principles. Let's start with the definition of this solid principle as a whole and where it came from. The solid principles are five essential guidelines of object oriented class design. Robert C. Martin developed these solid principles in his paper named Design Principles and Design Patterns in the year 2000. He believed that successful software would always need to evolve, and without a good design principle, software becomes rigid and fragile, which makes software impossible to enhance and maintain. In other words, these principles are a set of rules and best practices to follow while designing a class structure that enhances overall software design by making the code more maintainable and scalable. As you might already know, the acronym SOLID stands for Single Responsibility Principle, Open Closed Principle, Liskov Substitution Principle, Interface Segregation Principle, and Dependency Inversion Principle. We will go through them one by one in this video. And let's start with the first one on the list, the Single Responsibility Principle. The Single Responsibility Principle, or SRP in short, says that a class should have only one reason to change, meaning that it should only have one job or one responsibility. Let's see this in action. Suppose there is a user class with some fields such as name, email, the constructor, and the getter setter methods. Also, suppose that some developer has introduced a method to display the user in YAML format in the same class. This is a bad practice as this violates the single responsibility principle. If a requirement comes for changing the display format or adding a new format such as JSON or HTML, then we will have to change the user class every time we have to make changes in the display format. According to SRP, the user class should not be changed unless the user definition has changed. Solving this is quite easy, as you might have already guessed. We can solve this by removing the method which is responsible for displaying the user object from the user class and move the displaying responsibility to a separate class which is only responsible for managing the output format. The SRP is a relatively basic one that the most developers already follow while developing code. It can be applied to classes, software components, and microservices. The advantage of applying SRP is that it simplifies the classes, which makes testing and maintenance of code easier, which leads to a more efficient software enhancement process. Let's move to the next one. The next principle we will be talking about is the open closed principle. Let's start with the definition. The open closed principle states that the class should be open for extension but closed for modification, meaning that you should be able to extend the behavior of a class without modifying it. Let's understand this with the help of a code. Suppose we have a discount calculator class which calculates different types of discounts based on the customer type. As you can see in the code, that the discount amount is calculated based on the if-else condition. Suppose we want to extend the functionality of this class to calculate discounts for different types of customers, for example, new customers, then we will have to modify this class and add a new else if condition. This is fairly simple example, so you may not realize, but changing the class every time and adding a new else if statement can introduce bugs to the working code and can be difficult to manage if the conditions grow bigger and bigger. Let's see how we can improve this by applying the open closed principle. To solve this, we can use an abstract class which contains an abstract method called calculate. All the types of discounts that we want to calculate can be divided into classes, and they can extend the main discount class and provide implementation to this calculate method. Further, the calculate discount class in the discount calculator class can accept the object of the discount class in the argument. Under the hood, the object will refer to the exact discount which is applicable for the customer, and the calculate discount method will be able to call the calculate method using polymorphism to calculate the discount. In future, if we want to add another type of discount, for example, new customer discount, we can simply create a new class for this and implement the calculate method, and we will be able to extend the functionality of this discount calculator class without modifying any existing code. Next, in the business logic, this can be used as shown in the main class. With the help of runtime polymorphism, the calculate discount in the class discount calculator will automatically call the calculate method of the appropriate discount type using the discount class passed in the argument. The open-close principle recognizes that you may need to add or change something to existing and well-tested classes, and there are risks associated with every change which can create problems or bugs. So, by following the open-close principle, your code becomes easier to maintain and revise. The open-close principle is commonly implemented using abstract classes and interfaces, which allow you to use runtime polymorphism by polymorphic substitutions. Let's look at this Liskov substitution principle next. The Liskov substitution principle states that the subtypes must be substitutable for their base types without altering the correctness of the program. This simply means that given that class B is a subclass of class A, we should be able to pass the object of class B to any method that expects an object of class A, and the method should not give any weird output in that case. We will take the classic example of rectangle and square class to understand this principle. Suppose we have a rectangle class having fields width and height, and we have a setter methods to set the width and height and a get area method in this class. Next, let's suppose that the square class extends the rectangle class. Since a square is just a special type of rectangle where the width is equal to height, so we set both width and height to the same value in both the setters. Suppose a tester who is testing your code has written this test class. In the first test, we create a rectangle where the width is 2 and the height is 3 and call getAreaTest. The output is 20 as expected since the height is set to 10 inside the function. But things go wrong when we pass in the object of square class. This is because the call to the setHeight function in the test is setting the width as well, which results in an unexpected output. The tester will come back to you saying that the code is not giving the correct output. To solve this, we can introduce an interface called shape with an abstract method getArea. So any class which implements this interface will also have to provide an implementation for the getArea method. Now, the rectangle class and the square class can implement the shape interface, and the objects of the rectangle class and square class can be used interchangeably without any unexpected behavior. The Liskov substitution principle is perhaps the most difficult to understand out of the 5 solid principles. So let's understand this with the help of a simple illustration. Suppose we have two classes, class A and class B. Class B inherits class A, and we have an object O1 of class A and object O2 of class B. And we also have a program which accepts the object of these classes. So, according to the Liskov substitution principle, when O1 or O2, any of these objects are given to the program, then the program should give exactly the same output. The point of the Liskov substitution principle is to ensure that derived classes should extend the base class without changing the behavior. Following this principle helps you to avoid unexpected consequences of changes by enforcing consistency so that the parent class objects or its child class objects can be used in the same way. Hope this was clear. Moving to the next principle, we have interface segregation principle, or ISP in short. This principle states that clients should not be forced to depend on interfaces they do not use. Let's see a code example to understand this in more detail. Suppose we have a printer interface which contains methods print document, scan document, and fax document. And we have a simple printer class which implements the printer interface. As you can see, the simple printer can only print documents and is forced to override the methods which is not relevant to the simple printer. This is the violation of the interface segregation principle. To solve this, we should create 3 different interfaces so that the printer classes are free to implement only those interfaces which are relevant to them. For example, the simple printer is free to implement only printer interface and provide implementation for the print document method, while multifunction printer can implement all the other interfaces which are relevant to it. The interface segregation principle for solid programming states that it is better to have many smaller interfaces than a few bigger ones. Let's move to the last principle on the list. The next principle is the dependency inversion principle, or DIP in short. It states that the high-level modules should not depend on the low-level modules, rather both should depend on abstraction. And abstractions should not depend on details, and details should only depend on abstractions. Let's try to understand this with the help of illustrations. The class, which is represented as a robot in the diagram, is directly dependent on a concrete class represented as a light bulb. The class can only operate the light bulb and cannot operate any other device because the class is tightly coupled with the concrete class light bulb. So this can be solved by inversing the dependency of the program. In this case, all the switchable elements now implement the switchable interface, and the dependency of the program is inversed to an interface called switchable, which enables the program to be able to control all the elements which implement the switchable interface. This makes the whole design to be loosely coupled and solve the problem. Let's see how this is implemented in Java code. Suppose we have a light bulb class which has the functions turn on and turn off. And we have a switch class which depends on the concrete light bulb class. So as you can see here, this violates the dependency injection principle, as the switch class is directly dependent on the light bulb class and can only operate the light bulb. This can be solved by making a switchable interface so that all the elements which can be switched implement this interface, and inverting the dependency in the main class from the concrete implementation of light bulb class to the newly created switchable interface. The main aim of this principle is to design decoupled software modules. The advantage of following the dependency inversion principle is that it will make the code more flexible and reusable. When you implement solid design principles, you create systems that are more maintainable, scalable, testable, and reusable. Mastering solid principles not only improves the quality of software, but also enhances collaboration among developers, as well-maintained code bases are easier to understand, debug, and extend over time. Thanks for watching the video. Please share your feedback and comments. Hope this video was helpful for you, and I will see you in the next video. Till then, goodbye.